The Alphabot. In a past video, I showed off many capabilities of this remote-controlled car, starting at the Alphabot being able to determine its own position and orientation, pathfinding, and navigation. Since then, many improvements have been made. Apart from major performance, memory and hardware optimizations, including an updated PCB and using the ESP32's ultra-low power coprocessor, wheel encoders and an obstacle scanner were added, and the accuracy and precision of the positioning system were significantly improved. And everything can be replicated thanks to the extensive manual. In this video, I will walk you through these new enhancements. Starting with the state of the positioning system showed in a previous video. It used positioning modules by measuring the distances to fixed anchors in the room and then calculating the position with triliteration. This relies on precise distance measurements. Unfortunately, the positioning modules are not perfect. Therefore, the measurements fluctuate, causing the resulting position estimation to fluctuate as well. In my search for a solution, I came across a mathematical procedure called the Kalman filter. A Kalman filter takes in one or more different noisy sensors and tries to estimate a filtered result. In my case, I already had one input to the Kalman filter, the raw position measurements. For a second sensor input, I implemented wheel encoders that measure the speed at which wheels turn, meaning the vehicle knows how fast it's moving. And thanks to the compass, it also knows which direction it's moving in. So combining the wheel encoders with the compass provides precise relative movement measurements. Feeding that into the Kalman filter alongside the raw position measurements yields impressive results. The white outline of the vehicle represents the estimated position. The green dot shows the true position of the vehicle. The estimated position follows the true position closely, with virtually no delay. But how does this work? The precise movement measurements of the wheel encoders with the compass allow for an immediate relative position estimation. This alone works very well, until it slowly begins to deviate from the truth due to small inaccuracies that add up over time. To correct for this, the raw absolute position measurements are factored in with a very low weight, just enough to bring the position estimate back on track. Both inputs of this Kalman filter are important. If we were to only use the wheel encoders with the compass, the positioning would be precise, but it would deviate from the truth over time. On the other hand, using only raw position measurements provides reliable results with less precision. The Kalman filter combines the best of both worlds. With this much better positioning system, navigation was further improved to prevent collisions with obstacles. Another feature added to the Alphabot is an obstacle scanner. This uses the TF Luna LiDAR distance sensor mounted on a stepper motor that moves the sensor from side to side. The obstacle scanner can be used to build a map of the surrounding area. The Alphabot now has two stepper motors, both controlled by the ESP32's ultra-low power coprocessor, leaving the two main cores free to run other code. The two stepper motors are driven by a single chip sitting on an updated version of the PCB. The new PCB is much smaller because it gets rid of the secondary ESP32 altogether. Thanks to optimizations, the Alphabot now gets by with a single ESP32 as its brain. Everything you've seen here can be replicated by following the build instructions and the user manual in my public Git repository. The link is in the video description. Thank you for your interest in the development of the Alphabot.